Hi, we are from CE2 Group 5. The topic of our presentation is isomerization of light gasoline and m-xylene to o-xylene process. In this video, we will focus more on m-xylene isomerization. Generally, m-xylene isomerization will produce two products which are p-xylene and o-xylene. In this presentation, m-xylene to o-xylene is the main reaction. This process takes place is because the high demand on o-xylene more than m-xylene. O-xylene is more valuable than m-xylene because it has wide range of uses such as producing phthalic anhydride. The catalyst that will be used in this process is ZSM5 zeolite catalyst. It was observed that the m-xylene activity and selectivity with respect to the yield of o-xylene is more consistent with the presence of medium pore of the zeolite crystallites.
Moving on to catalyst screening. The preferred catalysts used for isomerization process are zeolites. In an article, an experiment of m-xylene isomerization is conducted with 4 types of catalysts and the results are shown in the table. The high basicity of m-xylene molecule helps the diffusion of m-xylene through the 10 rings and further isomerization. The positive effect on selectivity is due to the low prototonic acidity of the catalyst. IM catalyst shows the highest acid sites, thus it is not preferred to be used in this process. The PO value is the ratio of P to o-xylene amount presented in the product mixture. Hence, the lower the PO ratio value, the higher the amount of o-xylene production compared to p-xylene. As shown in the table, the diffusion of o-xylene molecules in zeolite TNU10 channels is strongly inhibited and the highest p-xylene selectivity is observed. However, in zeolite ZSM5 and TNU9, o-xylene has higher yield and selectivity compared to p-xylene. Further research found that the structures of TNU9 and IM5 delivers a serious constraint for o-xylene molecule diffusion and its further conversion. To conclude, the results shows that ZSM5 catalyst is the preferred catalyst to be used for m-xylene isomerization in producing o-xylene.
For the reaction mechanism, all zeolite used were found as highly crystalline structure as confirmed by product X-ray diffraction. The overall catalytic activity is therefore ruled by the pore topology due to the zeolite undermined of the amount and strength of the SiOHL group. For the first catalyst, which is the ZSM5, accumulation in the pore of zeolite proceeds in the earlier stage than the substrate molecule consumption. It evidences the shape selective acting of the structure since m-xylene only absorbs on acid center only. For the second catalyst, which is the M5, reaction occurs in the first 4 minutes to produce obvious product o-xylene, also the intermediate species. Considering the transformation of o-xylene, apparently it is related to diffusion restriction in micropore system. Compared with TNU10, IM5 has faster accumulation of the isomerization product. This third catalyst which is the TNU9. It is not limited due to the transformation ruled by the isomerization, not perturbed by the absorption process. Only in the first 4 minutes, the correlation within the o-xylene can be found. 10-ring channel in the structure of TNU9 and IM5 delivers serious constraint for o-xylene molecule diffusion and its further conversion. Lastly, TNU10. Only in the first 4 minutes can be concluded that the product formed at the expense of m-xylene provide comparable steric constraint for transformation. This can also be implemented for the catalyst IM5 to differentiate disposed zeolites. Is the sequence of the changes taking place on the surface. Consumption took place in the first period of the process due to the formation is strongly influenced by its geometry. To summarize, intermediate species formation is strongly influenced by the geometry of internal cavities of the respective zeolites.
Moving on to the determination of basis for reactor, for isomerization of m-xylene to o-xylene, for the feed, 1 to 4 mole ratio of m-xylene to hydrogen is assumed. Besides, pressure required for the reaction to occur is at atmospheric pressure, while the optimum reaction temperature is 553 Kelvin. In addition, weight-hour space velocity for this reaction is assumed 17.5 per hour, with reaction conversion of 0.92 weight%. After isomerization occurs, composition of m-xylene drops to 90.8 weight%. The estimated products obtained from this reaction are 3.7 weight% of o-xylene and 5.1 weight% of p-xylene, with side products which in total of having 0.8 weight%. The selectivity of this reaction is assumed to be 0.95 weight%.
Assalamu alaikum and hi, I am Emad Rayhan. I'm going to represent the reactor selection and design. For reactor selection, we will be using moving bed reactor because we are considering the regeneration catalyst process. where we need to withdraw and regenerate the catalyst during the operation of the reactor. Before going to modeling of the reactor, we need to consider some assumptions as shown in the presentation. For reactor modeling, we will be using mass and energy balances as shown in the presentation. For reactor simulating, we will be using IBM basic programming. After simulating the process, we have the results 5.1 and 5.2 figures, where we can see that the productivity will decrease and the desorption consumption will increase along with time and reactor length.
As a summary, in catalyst screening, the catalyst is chosen in terms of basicity of m-xylene, selectivity, pO value, and acidity of the catalyst. ZSM5 is determined to be the most suitable catalyst. Next, reaction mechanism. It shows that the desired reaction is the first period of the process in IM5, as the conversion of m-xylene is the most rapid. Determination of basis for reactor design. ZSM5 zeolite is selected as the basis because it is highly selective and stable. Moving bed reactor is chosen as the reactor design, and it is proven with the calculation of mass balance, energy balance, and other parameters of the reactor. That's all from us. Thank you.